lights on here. Okay, thank you. So actually I'm going to talk about three things. I'm going to talk about kinetics, of course, just to introduce that. Then a little short note on what we've learned, and then moving on to video understanding, I guess. That's what's going to happen. So kinetics, I guess most of you are familiar with it. I'm just going to overview it a bit. This is an example of some of the classes from Kinetics. Archery, dancing, horse riding, and Kinetics consists of these 10-second clips which come from YouTube, okay, from classes. And the reason we built Kinetics was because of the success of ImageNet. So we'd seen that in ImageNet, it allowed two things. ImageNet allowed architectural development, having this large data set of supervised annotated images. So you had AlexNet, you had Inception, you had VGGNets, you had ResNet, etc. That it enabled that. That was one thing, and it also enabled transfer, that once you trained your network on ImageNet, then you could use it for other tasks like object category detection. Okay, and we wanted to see, well, we really wanted to do the same thing for actions and for videos. So it was built with this in mind. So we built this large data set, human action recognition. Always has to be human actions. They're short 10-second clips, trim videos, and we wanted the data set to be large enough to be used for architectural development. That was one of our goals, and also to, if you trained on this data set, then you could use it for other tasks like visual question answering or segmentation, etc. That was our reason for doing it. And we've released 3 versions of it so far. The first release was in 2017, where we had 400 different human action classes with at least 400 clips for each one, 3,000K in total. And the important thing about the clip is for a particular human action class, you know, like waving or something like this, each of the clips comes from a different YouTube video. Okay, so what that means is, because each one's from a different YouTube video, you have a huge variety in the people that are doing it, the lighting, the clothes, the camera angles. Okay, so that's what we went for. And then last year we released a bigger version, Kinetic 600, and this year we released Kinetic 700. So we're up to about 650,000 clips now. Okay, so I'll show you. This is where I show you some examples. That's always a fun thing to do. So we can basically divide Kinetics into 3 categories. There's person doing actions on their own, so you know, the waving. Then there's the person-person interaction, the hugging, etc. And then there's the interacting with objects. So first of all, these are singular actions. So, you know, pumping fists, shaking. I'm not going to do all these ones. Shaking heads, and then a few more ones. This is sporty actions where they're quite similar. They just differ very slightly. Long jump, triple jump. Then some person-person actions. So here, shaking hands. Starting back, person-person interactions, person-object interactions, playing violin, playing trumpet. I'll move over here a bit. And now here's folding clothes, folding napkins. So this is the same verb but different nouns. And now here's the same noun but different verbs. Okay, so we tried to do a bit of this. And then, as we increase the size of the data set, we don't really have a hierarchy in Kinetics. It's quite a flat list of action classes. But we just increased everything. So here, there's more single human actions, headstands, tiptoeing. They're quite fun, really, some of these things. This is what people put on YouTube. So this is just on the face, raising eyebrows, crossing eyes. And now this is twiddling fingers, cracking knuckles. And so it goes on. So now Kinetic 700, we get more classes, and now that we're starting to get a bit bizarre, because you have to come up with these. This is not too good here. But being in zero gravity is not a bad one, actually. I think that's not bad. And then it gets really random. So this is contact juggling, which is a very beautiful action. I didn't know about this till we saw this. And then there's the sort of, we saw before, wrestling with lions. We have alligator wrestling in Kinetics. So. It's just amazing what you do. Anyway, so we've got this list, and then in terms of, so did we succeed in what we want to do? And I think we did succeed in our 2 goals, actually. So we wanted to encourage architectural design, or enable it, actually. And what we've seen is a whole host of different architectures. I just mentioned that we did the I3D, and then there's been a sort of 3-letter following on from this, which is improve things. So we do have a sort of a very good set of spatial temporal or two-stream networks that can be used for human action recognition and generally for video understanding. And then in terms of pre-training and transfer learning, again, I think we succeeded. I'll talk a bit more about training on kinetics and then doing action classifications on these existing benchmarks, UCF 1H, MT51. But training on kinetics has also enabled spatial temporal localizations on these data sets, and even beyond human actions, i3D features have then been used for medical scans and used for detecting cancer. So it's gone further than human actions as well. Okay. So I think we succeeded there. In terms of UCF and HMD51, these were the data sets, and just the sort of boost. You remember with image, when you trained on ImageNet, you got this big boost on Pascal, and we wanted to see the same thing, train on Kinetics. Do we get a big boost on these existing benchmarks? And this is before training on Kinetics. So these are algorithms or networks trained on ImageNet, and yes, there was a nice gradual increase. ImageNet, deep learning gave a boost, but then when we train on Kinetics 400, you get this big gap, and that's what happened by training on these larger data sets. Okay, so that was successful. And I don't know, just draw attention to this very nice website which aggregates, by some of the organisers here, aggregates all the different benchmark performances. Very, very useful, I think. Jason?
Do you have a sense, because it's larger because of the size, or larger because of the number of classes?
Do you mean...
this jump hill you're talking about, just pure video?
I don't know the answer to that thing. I mean, I haven't done that experiment where we trained on half. So on ImageNet, people have trained on half the amount of same number of classes, half the amount of data, and you can get similar forms. I haven't done this experiment here, so I can't quite answer that question.
How do you choose the class names?
Imagination. So Cordelia's asking, how do we choose the class? We're open to suggestions, really. I mean, I'd say we steal from other data sets to begin with, and then we innovate, and we even got the Turkers to suggest class names, and that was quite useful for getting up. So we'd pass them on, say, is this a such and such? And they say, no, it's a such and such, and we'd look at statistics on that, and that was one way of getting class names.
Nothing systematic.
No, we don't want it to be really, because really the class names don't matter too much. From our point of view, it's a pre-training that's useful, or it's once you've trained your network, then you can use it for other things.
So did you have 1,000 classes to just match with the ImageNet? Like you have 700 now?
That's our goal. We might not get there, in fact. Okay, so, but it's not perfect, it's a limited data set. One of the limitations is the fact that it's good for continual actions, the sort of drummings. It's not good for actions that have a start and finish. Okay, it's not good for these progression actions. And this is a consequence of the way we collect it, so I'm going to go through that. So we start with a class list, as we said, and this class list is text. We then use this text to go to YouTube and do a text search. It's all text-based. And say the text was playing drums, we'd now have hundreds or thousands of YouTube videos which we find with a text search. Then we have to localize the action inside that, and that's done very loosely. We have an image, a frame level classifier, which would look for, say, drums, just to give us a hint. And then we tend to take a few 10-second clips from each video, and it goes out to mechanical Turkers, and they say, each one's seen by multiple Turkers as usual, is someone playing drums for this 10-second clip? And after that, there's some data set cleanup, etc. But the point is that there's real no effort to localize. It's just we use these very loose image classifiers. This does not let us do actions that have a start and a middle and a finish, an end. It's not suitable for that. So if you want to do things like that, then you have to use data sets like something, or instructional videos, or cooking videos, etc., as we've seen earlier, where you really are dealing with something which goes over a long temporal sequence. Okay, a brief thing on what we've learned by doing this. So I had a whole bit in the talk here about optical flow, but Case has done that very well in his talk this morning, so I'm just going to add something to what Case said, rather than go through it all again. So we know that two-stream networks always give a boost, and here's some results from 2018, so last year. And here, if you look at this column, this is RGB only, so usually a 3G convolution or something like that, giving performance on Kinetics 400, and then adding in a separate flow network, there's always a boost of a few percent, so Case made this point. Okay? And we know from Dutran's talk this morning that actually we're up at sort of 82 now on this, so that's what happened this year. Right, so Case explained how he had a network, which is this 2-in-1 network, where you could use the flow to modulate the RGB stream, and that gave a boost. Okay, but I just wanted to mention that some other ways of doing that, before we do that, is what we know from these results is that the RGB networks, so say the 3D convolutions, they're not getting all the juice out of the motion, because if you add in flow, you get a boost. Okay, so we know that the current generation of networks is not getting everything it could do from data. That's what we know. Okay, so as I said, Case had a way of doing it. There's another way of doing it, which is sort of a teacher supervision. So here's one paper that did it. So you have a RGB stream, so this would be a spatial temporal convolution coming in, and this is your one stream, and then you supervise interactions, but at the same time, during training, you have optical flow and a temporal stream, and you do a distillation, so you force this network to be able to also predict optical flow, essentially. So now you're saying to the network, you better be able to predict optical flow. That's what you're saying, okay? And you can do this by distillation, or you can do it by supervision. But if you do that, then here's the result. Network at all. You don't have to compute flow at test time. So this is a good lesson. Right. So now I'm going to go on to the last part of the talk, and I've got a nice link. So here's my link to the last part of the talk, which is going to be video understanding. So I'll show this again. So here's Charlie Chaplin walking along. I'm sorry about the quality of this. I didn't get a good example. So you can understand this. Completely what's going on here, completely understand the silent film visually, right? How do they do this? They did this by going backwards. It's Dima was talking about going backwards video, so obviously you don't film this going forwards because you get killed. You film this going backwards. Okay, that's how he did it. Right, so that's silent. You can understand things completely by silent. Here's my link to why have I included these two films here? What's common about these films? Sorry? Dancing is common, but not the answer I want for the link. For the link. Silent films. Where do you think I'm going? Both these films are about the coming of sound to movies. Okay, it's coming to sound to talkies here. That's what these films are about. Okay, apart from other things. Okay, so the link is, as we've heard from Rahul right at the start as well, that that film, video is multimodal, and we should be. Now I'm moving on to the video understanding part of the talk. Okay? So for video understanding, it's absurd not to use the other modes which are present. Okay, of course we've got video. We can do things from video alone, but we've also got audio, and we should be using all of these for our video understanding. And I'm going to break that down a bit, because even just with audio, we can break that down into speech, what people are saying, also ambient sound around, so people might be speaking, but there also might be noise of tools they're using. Dima was talking about how audio is so helpful for understanding what the action is going on. Might be dogs barking. You've got all that in the audio stream, and we can break down the video stream as well, not just like having I3D features or some spatial temporal features. We can break it down into the objects, the scene, the actions, the faces of the people, face representations, and also the text. And the text can be overlaid information like this, like the banners or etc. Or it can be scene text, just text that's in the scene. And we should be using all of this for video understanding. Okay. Question is, how do we use it? But we'll come to that in a minute. And the reason we should be using all of this is we know how to do it. We know how to build networks that can represent objects. We do ResNet and we train it on open images or ImageNet. We know how to do this. We know how to do scenes based on places. We know how to do actions. We talked a lot about that. We know how to do faces. We can do face detection and OCR, etc. We know how to do all these things individually, and we have data sets which let us train for this individually. So, by the way, there's a poster on this in the lunch sessions, and that's the work I'm going to talk about. So, how do we encode it? That's the issue. We know how to get it, and the work I'm going to talk about is by Yang Liu, Sam Aboni, and Ashna Agrami, and these two are here today. So they're talking about their poster. So, how do we encode it? So, we're going to look at the task of retrieval. So, the task here is you have a query, a text query, and you have a big pool, a large-scale pool of videos, and you want to find the video, the clip in this case, which matches that query. Okay, that's the task. So it could be a text query like you're cutting tomatoes and you spray yourself, with red, and that's bad. You want to find a clip like that, for example. So I'm going to flesh out the point about using all the modes, all the information streams. So here's a query. Two men are sitting at a table discussing Christianity, God, etc. And then this is the clip that fulfills that query. How do we know that? So obviously here are two men sitting at a table, but there's no way we can know what they're talking about unless we listen to the speech. So I'm going to play the sound and see.
So they can ask us questions. She says, I'm confused about post and pre-tribulation rapture. Both sides have a good argument.
Okay, so the point here is you need the audio to answer this query.
Both sides have a good argument.
Here's another one. So the query is kids reacting to a video of President Obama giving a speech. Okay, so let's look at this this clip. I'm going to play it in a second, but look at what's in the clip. Well, first of all, you've got President Obama, and so you can recognise him from his face. It actually says Obama here, so you can recognise it from the text. And it's talking about kids reaction, and look, it says kids react here. So if you've got the text, if you do scene text spotting, you solve this. And if you play it,
who have fought so long for their basic civil rights.
I don't even know what to say.
Families will now be recognized as equal to any other.
Civil rights.
America.
So you also have the voice. You have Obama's voice. You could recognise it from, and what they're saying as well. So all of these cues are there, and for video understanding, we've got to be using them all. Okay. So then, how do we use them? Here's going to be an example of how we use them. Of course, there's lots of work to do here. And how we're framing this is that we're going to have an embedding for the video, and we're going to have an embedding for the text, and those embeddings are going to live in the same space. And this idea is really explained very well in this paper by Antoine Mitch and Ivan, who's here, and Joseph. If you want to sort of see this framework explained and done very well, you should look at this paper. So the idea is you've got these things in a common embedding space. And then at runtime, you have your query, you put that in the embedding space. You have many other video clips also in the same embedding space, and you simply do nearest neighbours ranking of all these embeddings against your query. That's how you do your retrieval. Okay? And you train this with a ranking loss. You have a large data set where you have, say, captions and video clips, and you learn this embedding space with a ranking loss. Okay. So how do we get this video encoding? And the way that we've done it in this work is something that's called collaborative gating, which of course I'm not going to have time to explain. I'm just going to show you a bit how it's done. So we have all these experts, which could be scene text, we've represented by a vector, faces represented by a vector, audio represented by a vector, speech represented by a vector. We've got all these vectors, all these embeddings. We want them to be aware of each other. And we want to be aware of each other so that they can be discriminative when we combine them, and also that they don't throw away specific information. Like if there's some scene text, we want to keep that. So to be aware of each other, they have to sort of talk to each other, and the way it's done in this paper is we take a particular embedding and it looks at all the other ones pairwise. And based on all those other embeddings, speech against scene, speech against text, it builds a attention vector. And this attention vector is then used to gate that vector. Okay, so that's how they talk to each other. And then you concatenate all these vectors once they've been gated and use them for retrieval. And in terms of how well it works, this is on 4 different data sets which have retrieval, some based on YouTube, some based on films. Low is good here. This is a medium rank, and you can see the difference it makes just on each of these. These are the state of the art, and in each case it gives a substantial boost over the state of the art because we're able to use this specific and this discriminative information. Okay.
It's important to have the pairwise.
There's a way we're doing it. I mean, I think there's just sort of one way of doing it, just a light way of combining this information.
Because you could combine them all together.
You definitely could. Cordelia thinking how to improve it. You definitely could improve on it. There's just a way which is better than the existing ways. But the important thing is you've got these experts which are very easy to train. How do you combine them? And this is one way. Okay, so that's my video understanding part. You must use all the modalities if you can do video understanding, and here's one way of combining them, but there's lots of research to do here. So to finish, you wanted some challenges. So challenges, we've heard these before. We need to do temporal sequences, yes. Of course the future should not be supervised. I mean, we need to self-supervise, of course. I mean, that goes without saying, so I didn't say it. And the big message is that for video understanding, we multimodality. I draw your attention to a workshop that's at ICCV on holistic video understanding, which is related to this. One of the organisers is here.